In this video, we're going to continue our look at all the different ways that the derivative can be used to answer questions that go beyond just, a tangent line, or now we can even say a rate of change. And over the next few videos, what we're going to look at is this idea of curve analysis, right? So we're going to analyze curves, and we're going to use the derivative to identify when a function has certain properties, right? So we have a few properties to go through, and the properties that we're going to talk about in this video are the properties of increase and decrease. So in a nutshell, what we're going to determine is when is a function increasing, when is a function decreasing, and what would cause a single function to change from increasing to decreasing, and how are all those properties related to the derivative. So first, what's really nice about these particular properties is that they're very visual, right? They're visual, and so we can introduce all these ideas by certain sketches. So I'm going to sketch a function, and it's going to be continuous. So I'm going to do it in one. I'm going to try to make it a nice continuous motion. Like this. So there is our function, right? So this is the graph of y equals f of x, right? So when we talk about increasing and decreasing, we're talking about parts of the function or the graph of the function that are going up, right? So here, here, and then maybe a little bit there, right? So these sections that I've kind of indicated with the blue arrows pointing up, those are portions of our graph that we would describe as being increasing, right? Because essentially what we would say is as x goes from left to right, starting let's say at this x value here, as x gets bigger, so does your y. So when we say something is increasing, we're actually referring to the dependent variable y, right? And then similarly, for values of x in this interval, then our y values are getting bigger. And then similarly here, our y values will be increasing, right? And then on the flip side, we can see that there are portions of the graph where as x gets bigger, the y values get smaller, right? So as x goes further to the right, then the y values go down. And here's another portion of the graph on which we would say that the graph is decreasing. Now here, this part of the graph, well, it's neither going up nor down. So it's like for these values of x, right? For certain values of x, it's like constant. It's just it's horizontal, right? So let me go ahead and actually write in the terms that we'll use quite a bit. So constant there, and I'll just write it along one of these. So like here, increasing, and then here. So it'll be interesting writing this downwards. But hey, looks like I can do it. Decreasing, right? So again, these are the properties that we're going to look at first, like when are the y values going up, when are the y values going down, when are the y values constant, right? So we're going to do two things. We're going to first give a formal definition of this, right? So this is certainly nice, a nice intuition to get an idea of what these properties are. But we can't really do much with just, arrows pointing up, arrows pointing down. We need to be a lot more precise. So we'll first give a definition of what it means for a function to be increasing, decreasing, or constant on an interval. And then we will see how do these properties relate to the derivative, right? Because that's the thing. Ultimately, what we want to be able to do is if, let's say, this graph goes away, let's say this graph is gone, and all I have is the equation for my function. I want to be able to take this equation and then utilize the derivative of this equation and answer the question as to for what values of x is the graph going up, for what values of x is the graph going down, for what values of x is the graph horizontal or constant. All right, so that's an overview of our goal for today. So let's write down our first definition. So let f be defined on an interval. So I'm not even saying that it has to be continuous. I'm not saying it has to be differentiable. I'm just saying that it's defined, meaning for every value of x, there is a y, right? That's all this definition requires, right? So we need a function that's well defined on an interval, and let x1 and x2 denote points in that interval, right? So these could be any 2 points in our interval. So first, let's define what it means for a graph to be going up, right? So basically what it means is, in terms of what I'm about to write down, I'm going to use a pair of inequalities, but let me kind of verbalize the inequalities before I write them down. Increasing means that a larger x corresponds to a larger y. So if your x gets bigger, then your y will get bigger, right? So what does that look like? So let's call this one part A. So f is increasing, right? That's what we're defining now, on the interval if the f of x1 is less than f of x2 when x1 is less than x2, right? So again, remember that the f here is referring to the y values. So this is saying if your x1 is less than your x2 and the function is increasing, then the f of x1 would have to be less than f of x2, right? In a second, I'll draw some pictures specifically with these labels so you can see what we're referring to, and then based on those other graphs, we will then make a connection between this property and the derivative, right? But the connection should be fairly obvious when we see it, right? So f is decreasing, right, on the interval if I flip this, either I flip the inequality sign or I flip the f values to say, I could say it like this: f of x2 is now less than f of x1 when x1 is less than x2. So what this is saying, for the larger x, which is x2, it corresponds to a smaller y, right? So as your x gets bigger, then your y gets smaller, and that, again, that fits with our intuition about a y value that's decreasing. It's going down from left to right. And then C, the last one, is f is constant, right? Right, on the interval if you think about it, these are, saying that, for instance, this y value is less than this y value. This one is saying that this y value is greater than this y value. Well, if they're equal, right? So for a function to be constant, then the y values would have to be the same. So then it would be f of x1 would be equal to f of x2 for all points x1 and x2. So for all x1 and x2, right? What this is saying that the y value is the same, right? So there is no going up or going down, it's constant, right? So let's sketch another thing, but now I'm going to use three separate graphs. I'm going to sketch one that that will illustrate increasing, sketch one that will illustrate decreasing, and then sketch one that will illustrate constant. So increasing could be visualized this way, right? So let me now put an x-axis. So here's my x1. Here is my x2, and then this would be f of x1, that would be the y value, and then this would correspond to f of x2, right? So that's what this is saying. This y value, think of your y-axis this way, right? This y value is smaller than this y value, and this one corresponds to the larger x. So as your x gets bigger, your y value gets bigger, right? So this is the one that indicates increasing, right? And then similarly, let's draw one for decreasing. Well, yeah, let me just draw it going down this way, right? So again, here is x1, here is x2, and then over here we would have f of x1, which is now larger than f of x2. So again, that gives a sense that the y values are decreasing. And then I think you can see what's going to happen with the constant. So here are our two different x values, and this is what it would mean for the function to be constant. The y value never changes, right? So this would be your f of x1, which is the same as your f of x2. All right? So that's kind of the visual for these three specific properties, right? Now, as far as how this relates to the derivative, notice on this, even though I highlighted these two specific points, at any point here, if I draw the tangent line, as long as the graph is going up, these tangent lines are sloping upwards, right? So they're sloping upwards. Similarly, here, as long as the graph is going down, when I draw my tangent lines, let's say here, or here, or here, all these lines are sloping downwards, right? So, tangent lines that are sloping upwards, that corresponds to a function that's increasing. Tangent lines that are sloping downwards, those correspond to a function that is decreasing. And then look at constant. The tangent lines are themselves horizontal, right? It'd be like this. Because if the graph isn't going up or down, the tangent lines sure are not going up and down, right? So, then we know that the slope of the tangent line is the derivative, and if all these slopes are positive, then it means your derivative would have to be positive, right? So, so for all of these, your derivative, if I were to find the derivative of the function and plug in all these different x values, I will always get a positive number, right? Because the slope of the tangent lines are positive. So essentially, the geometry of the curve here is telling me what must be true about the derivative. And conversely, if this is true, if the derivative is positive, then all the tangent lines would have to be looking like this, hence the graph would have to be going up. So it's like this nice relationship between the geometry and the calculus. And then similarly here, all these red tangent lines, they have a negative slope. So if I were to take my derivative of f and evaluated at any of these x values, I will always get a negative value, right? And then over here, you can see what's going to happen. At all of these points, because the function is a constant, we know that the derivative of any constant is always 0. So the slope of all these tangent lines are 0. Hence, the derivative evaluated at any of these points is equal to 0, right? So it really is not a stretch going from this, what we would call a qualitative property, right? It's a property or it's a characteristic that a function has. And then that just analyzing, what has to happen with the tangent lines would then give us the connection with the derivative, right? And then that leads to a theorem, right? So, and this is the theorem that we will use quite a lot, right? So let's mark this. And basically, this is a theorem that we will use to help us determine whenever a function is increasing or decreasing or constant. It has to be one of the three, right? So, but now, in order for us to talk about the derivative, I can't just say well-defined. So I have to talk about the function being differentiable. In other words, the derivative would have to exist for me to say whether the derivative is positive, negative, or 0, right? So you'll see that the hypotheses in this theorem, it's a little bit more than the previous one where we were just giving a definition of the property. This essentially now gives us the connection with the derivative so that we can identify the property using the derivative. So let f be continuous, right, on a closed interval. In fact, the closed interval part can be dropped, and I'll make a comment about that in a bit. So let's say, and what I like to use the inequality notation for my interval just to emphasize that I'm talking about an interval of x values. So let's say f is continuous on this closed interval and differentiable everywhere inside the interval. So not necessarily at the endpoints, right? So, and differentiable on the open interval. And so the open interval will be where you exclude the endpoints. So like this, right? And then let's write down three characterizations of these properties now as they relate to the derivative. So if the derivative, right, is greater than or equal to 0 for every, or let's just say for all x, so for all x in this interval, so every real number between a and b, so in this interval, then f is increasing, right, on this open interval, right? So it's increasing on this interval. Actually, let me go ahead and state the open as well, because a lot of times the question will ask for an open interval, right? So if we can determine that the derivative is always positive for all values of x in some interval, then the function has to be increasing on that interval. And then similarly, if our derivative is less than 0 for all x in this interval, then the function must be decreasing, right? So f is decreasing on that interval. And then, the third one, this is something we would call like a trichotomy, when there are three possible things and one of them must be true. And then, so if your derivative is equal to 0, again, let's say for all x in our interval, then f is constant on that interval. All right, so that's it. So this now gives us a way. So if we have to find out where or for what values of x a function is increasing, decreasing, or constant, right? Then we're going to have to work with either this equation or these inequalities, right? So let's take a look at how this works. So let's look at an example of this. Right, so now no graphs, the graphs are gone, and what we're going to do is so determine the intervals of increase or decrease for this function. So let's say our function is, let's take a polynomial like 3x to the fourth plus 4x cubed minus 12x squared plus 2, right? And that's all we're given, right? And we have to determine the intervals for x for which this function is either going up or going down, right? And again, we're going to use our derivative to give us the precise solution, right? So let's start with our derivative, right? Because that's what this theorem is saying. We're going to work with the derivative. And I just want to make a note in our solution that this polynomial, we know that polynomials are continuous for all values of x, and they're also always differentiable for all values of x, because polynomials never have any holes or jumps, they never have any sharp corners, they never have any vertical tangent lines, and they never have any vertical asymptotes. So this function, so f of x, in fact, let's just say this, f of x is always differentiable, right? So f of x is always differentiable. In other words, the derivative always exists. So meaning it will always produce a real number. So that real number is either going to be positive, negative, or 0. And then we have to use algebra to then determine for what values of x will our derivative have these properties, right? Okay, so it makes sense. Let's start with our derivative. So our derivative here is 12x cubed plus 12x squared minus 24x, and then our constant goes away, right? So thinking of the three things that we have to do, right? We always start by finding the zeros of the derivative. You know, you take the first derivative, set it equal to 0. Let's do that. So let's first see if there are any values for which the derivative is equal to 0. So let's take our derivative, set it equal to 0. That gives me an equation. So we have this, and then plus 12x squared minus 24x is equal to 0. Well, if you look at this, we can factor out a 12x, right? 12 is a factor of each of the coefficients. X is a factor of each of our variables. So 12x is our greatest common factor. And then in parentheses, I have x squared plus x minus 2 is equal to 0, right? And then I look at that polynomial, this quadratic, and I see that it can be factored further. It is x plus 2 and then x minus 1 is equal to 0. So we have these, technically there are 4 factors, but the 12 can never be 0 because it is a non-zero constant, right? Now, if we write it down, we would say, well, either that factor is equal to 0, or x plus 2 is equal to 0, or x minus 1 is equal to 0. And then this gives me 3 possible values of x. So x equals 0, x equals negative 2, x equals 1, right? So these are the points at which the derivative is equal to 0. And we know that that would correspond to where we would have a horizontal tangent line. But these are only 3 specific points. So what it means is that at all other values of x, the derivative is either positive or negative, right? These are the only real numbers for which our derivative is equal to 0. So at all other values of x, the derivative is either positive or negative, which means the function is either increasing or decreasing, right? So how do we find those, right? So we can determine these intervals of increase or decrease. This is where our sign chart comes in handy, right? So I'm going to draw the sign chart, and because our polynomial has a domain that consists of all real numbers, I'm going to draw my number line going from negative infinity to positive infinity. And then I'm going to mark off these 3 special numbers at which the derivative is equal to 0. So I'm going to put my negative 2 there, then I'm going to put my 0 here. So not really drawn to scale, but just to give you a sense of, okay, here we have the values, so at these specific values, that's why I'm using arrows here, the derivative is equal to 0. Right? That's what the algebra here just told us. So then the question is, if x is between negative infinity and negative 2, is the derivative positive or negative there? Right? It can't be 0 because we don't have any other zeros of our function. We found them all. So that leaves either positive or negative here. Similarly, positive or negative here, positive or negative here, positive or negative here. So there are 4 intervals now that on which the function could either be increasing or decreasing. How do we tell? Right? Well, we tell by using our derivative and test points. So I'm actually going to do my test points in the form of a table now. So this is what I'm going to do. Let's set up our intervals here. And I'll take the intervals going from left to right. So the first interval, x is less than negative 2. All right, and again, notice I'm writing an open interval. I am not, well, I can't include infinity or negative infinity because negative infinity is not a number, right? So by default, this is never a point that can be included in your interval because it's not a specific point. It's just saying that, again, your x value can be more and more negative, right? Then the next interval, your x is between negative 2 and 0. Then your third interval, our x is between 0 and 1. And then the fourth interval is now where x is greater than 1. Right? These, the x is less than negative 2, x is greater than 1, these are called unbounded intervals. In other words, there's no lower bound on this interval and there's no upper bound on this interval, right? Just because the idea that it continues, our number line continues indefinitely, either in this direction or this direction. And then these intervals here, these are bounded intervals, right? Okay, so these are the intervals, and let's now identify test points that we can use, right? So I'm going to identify the test points that we're going to use to check to see whether our derivative is positive or negative, right? And then, so let me write down again what the derivative is. In fact, let me write down the factored form, right here. Let's write down this factor form. So we have the 12x times the x plus 2 times the x minus 1. So this is our derivative, right? And then let me now do a fourth column where we're going to have our conclusion, right? And this is the important thing, right? I mean, all this work here is to lead us to this conclusion, right? So we have to present clear evidence to say, okay, because of these facts, right? These are the conclusions that we must come to, right? So let's see. I'm going to pick a number between negative infinity and negative 2. So I'm going to go for negative 3. And then I'm going to pick a number. Let's identify all the test points. Then I'm going to pick a number between negative 2 and 0. So let's pick negative 1. Why not? Between 0 and 1, I have to pick a fraction. So I'm going to go for the wonderful 1/2. And then pick a number greater than 1. Let's pick 2. And then we're going to use these test points and see whether we get a positive or a negative number from our derivative. And it has to be positive or negative. It cannot be 0 because we've found the 3 zeros of the derivative. There are no other zeros, right? So when we evaluate this, we're either going to get something that's positive or negative. And I am not going to write down the actual number. I'm just going to show you all we want to be able to say is whether this derivative is positive or negative at each of these values of x. So look at it this way. And this is where the factored form is actually really handy, right? This factor is negative. This factor here is also negative. This factor here is negative, right? If I take negative 3 and I plug it into just the 12x, I'll get a negative number. If I plug it into the x plus 2, I'll get a negative number. If I plug it into the x minus 1, I'll get a negative number. So in fact, yeah, I shouldn't write negative 1 there. I didn't mean to write the 1s, just the negative signs. So if I multiply 3 negative numbers, voila, I will get a negative result, right? And let's repeat this process for the other 3 test points. So if I plug negative 1 into the 12x factor, again, I'll get something negative. If I plug negative 1 into the x plus 2 factor, look at that, I get something positive. If I plug negative 1 into the x minus 1 factor, I get something negative. So now, a negative number times a positive number times a negative number will always give me something positive. Again, I don't care whether it's 1,000 or if it's 0.0001. I just need to know if it's positive, right, or negative. Let's see what happens when I plug 1/2 in. So if I plug 1/2 in this factor, I will get something positive. If I plug 1/2 in this factor, I will get something positive. If I plug 1/2 in the factor x minus 1, that's going to give me something negative. So now this product has to be a negative product, right? And then finally, I think we can see that when we plug 2 into all of these, we're going to have a positive times a positive times a positive, which result in something positive. So what is our conclusion, right? Right? So the conclusion is this: our function is increasing, or well, yeah, so the function is going to be increasing wherever I have these blue plus signs, right, for those intervals, and then the function is going to be decreasing wherever I have these red signs for these intervals. So I'll state it for like each, essentially, since I have it in the form of a table, I'm going to state it with 4 separate rows right here. So f is decreasing for x less than negative 2. And then f is increasing For x between -2 and 0, f is decreasing. For x between 0 and 1, and then now f is increasing again for x greater than 1. So this this function basically it indicates this kind of sign pattern, right? Where your derivative goes from negative to positive to negative to positive, right? So again, the green points are the points where the derivative changes from a negative sign to a positive sign, or a positive sign to a negative sign, right? So these are points, specific points, where the derivative is equal to 0. But then the other parts of this number line, these are intervals, so entire intervals on which the derivative is either negative or positive, right? So we got all that information just by looking at the derivative, finding its zeros, and using the good old number line to create the sign chart, and then making our conclusion, right? So it's a pretty straightforward process. The only curveball that you could be faced is if the algebra to find the zeros is a little tricky. Like, what if the function isn't a polynomial? Then we might have to work with some of those transcendental functions, and we just have to up our algebra game to handle them. And I know we can. So I'll see you in the next video.